So, welcome to part three of Demystifying LLMs for software engineers. This is a re-recording and an extended version of the talk I gave at the One More Thing conference in Cupertino last week. My name is Roland Banak, and I am the developer of the Pico AI server. So, previously we looked at LLMs that you can run on your Mac or iPhone. And the models that are available right now, the open source models you can, are state of the art. There are really good ones. And we looked at the hardware needed to run these LLMs. Right now, the best value is definitely the Mac Studio, although the Mac Mini is a pretty good value as well. So, to recap, so the way I want to explain how LLMs work is differently than I learned it myself when reading like books and watching videos on LLMs. Because most of these books they go straight into the transformer part, and the transformers part is the most difficult part to understand in my opinion. And I think it is easier to learn how LLMs work if you treat the transformer as a black box. Like something goes in, something comes out, and instead focus on the steps needed before the transformer and after the transformer. And that's what we're going to look in the next few videos. So the way we're going to do that is to use a existing project called Llama 2 by Andre Caparti, the OpenAI. I'm not sure if he's a co-founder, but OpenAI's Andre Caparti. He has made a standalone C application that basically runs your whole LLM in a single executable. So when you look at like what files are needed to run an LLM, it I mean some argue that you need only two files. The weights, that's the bin file here in this case. For MLX, that's the safe tensor file, and like executable, the LLM inference engine. I'm arguing that it makes more sense to focus on three files. There are a few other files like JSON files usually, but the third file is the tokenizer. I'll explain in a bit why that is important to understand. So you might have noticed the size of the source of the inference engine called Ron.c, which is only 35 kilobytes. That's kilobyte, not megabytes, terabytes. 35 kilobytes, which is insanely small. So you might wonder, like, hey, is that because there's like a lot of like magic done in libraries? And the answer is no. If you're familiar with C, you see all like regular, very common libraries. The header files here are just a standard I/O. It's math, it's string, it's just the basic stuff. So apparently, it takes not a lot of code to actually run an LLM. And funny enough, the source is actually small enough to fit like into the memory of a 1982 Sinclair ZX Spectrum. You cannot run an LLM on the ZX Spectrum. You don't have enough memory for that, but at least like the source code can fit in it, which is kind of mind blowing to me because like if you have ever worked with like a database you don't have to learn language like SQL, for example, a computer language, to use an LLM. Instead, you can just ask your questions in English or any other language the model has been trained off. Besides that, it is basically like in theory you can like store all of humanity's written knowledge in a single LLM that can fit on a regular hard disk. It's not that hard to do that probably. And the LLM is able to understand like the information it's given, like creating links, making links between like pieces of information. And that just with a few hundred lines of code, that is absolutely incredible. And if you look at the code, here it is. Um, So here you can see the header files again. Again, standard header files. We're going into this in a bit. This is the structure of the bin file. We're going to go into that now. Then there's like a lot of matrix multiplications. That's the transformer part that we're gonna skip. And there are some methods at the end for the command line interface. Basically, like taking the arguments, command line arguments, and running the chat. Here you go. Here's a chat. Um, and there's a generate. If you use like any of the LLM APIs, you're probably familiar with that kind of API. Same thing here. So basically, it is just a few hundred lines of code, and that's all there's to it. I mean that is, in my opinion, is completely insane that it is even possible. So um, let's go back to our dictionary and explain a new technical word called tokens. So tokens are stored in the tokenizer.json file. So we're skipping the bin file for now. We'll go back to that later. Tokens are kind of in the ASCII or Unicode of LLMs. In other words, it is a numeric representation of a word. And what do I mean by that? Well, we can actually look in the file. So we have some JSON that I'm going to skip. And this is the interesting part that we have here. These are all the words that the LLM basically knows. So here we have the word item here, and we see things like underscore get, for example. Now, what does an underscore mean? It's pretty basic. An underscore means that this word will always be like the beginning of part of the beginning of a word. So there will be a space or a new line here, for example, or tab or something like that. This is not meant to be a word that is in the middle of another word, for example, because it is possible to combine these tokens. For example, if you look for the word Walkman, for example, you will not find it, but you will find the word walk. At least I had it just now. There it is, walk. And the word man, for example, it's right here. And there is um, another version that's just the word man. Let me see. Here we go. So that together, that makes the word workman, for example. If we scroll down, you'll see, and again, this is a few thousand, I think about 20,000 lines of items of words. You will see this at some point. Let me just see if I can find the beginning of this part. Oh my God, this is so much text. And this is still the index, and here we go, the merges. This is also pretty easy to explain. The merges are used to basically recognize and process, parse the tokens. So if it has, for example, if it's looking for, let's say, man, it has the word man. What it will do is a tokenizer will always try to find like the longest possible word token that's out there in the dictionary. So MA basically means if there is the first letter is an M and the second letter is an A, and there's a space in between here, then this will be seen as a single token. Now, man, for example, same thing. If there you find an M and an A, and also an N, then that will be one token, basically man. That's how you should read these files. So There are, yeah, there's a couple of special characters unknown. Let's see, that should be the first one. And here we go. No vocabulary. The token with index 0 is unknown. These are also special characters. This is beginning of text and this is end of text. Now, beginning of text you probably don't see that much, but end of text that is actually important as we're going to see later on in the talk. Um, let's go to the next word, and that is embeddings. So tokens are ASCII or Unicode, and embeddings are kind of GPS coordinates. GPS coordinates of what? Well, GPS coordinates of tokens. And the way to see that, and we can actually see that if we go back to the C file. As I said earlier, this struct is the format of the bin file. So it has a lot of weights, as you can see. That those are just matrices with like many floating point numbers. This is, by the way, the transformer. I mean, again, it's a read-only file. It's fixed. This is how the model has been trained. And one part of the training is to make sense of the tokens. What do I mean by that? The tokenizer that's used for most LLMs is one of the many existing tokenizer structures. So many of these models that exist share like the same tokenizer. And when a model is trained, it basically tries to cluster words that it sees often together or are referring to each other. It clusters in its kind of mental model that it creates. And that's basically the embeddings table. How it looks on a byte level, it is pretty simple. And the embeddings are basically vectors of a certain dimension. I will get to that in a bit. They have a certain size, floating point size, and the number of embeddings is exactly the number of tokens. That's the vocab size you see here. Again, for every token in the tokenizer JSON, there is an embedding in the embedding table. That's part of the bin file. The Let's actually go here. So yeah, um, the thing to remember is and I try to kind of visualize how the bin file works. So you have like the black part here, that is the embeddings part. And then the white part is the other part. That's the weights part. Um, One thing to remember is that for the embeddings is always like fixed because you have a fixed number of embeddings and you have like a fixed number of dimensions for these vectors. So it means that for smaller models, usually the embeddings is like a bigger percentage, a bigger portion of the file than the weight, the transformer part. Um, so it might have been a little bit vague what I mean by vectors and GPS coordinates. So let's dive into that a little bit more. So here we have three tokens: Paris, France, and Italy. And the way to think about it is in a 2D or 3D plane. So each of these words has, or each of these tokens has a vector. Again, in reality, this vector will be something like a few hundred or a few thousand of dimensions. That's kind of hard to imagine for an average human being. So we're going to simplify it a little bit in a 2D plane here. And the interesting thing is that you can do math. with these vectors, which, for example, you can have a Paris, you can minus France plus Italy. So you subtract France from Paris and then add Italy. That result is a position where the question mark is placed. And if you look what word is in that position, you probably guessed it by now, that word is indeed Rome. So that's kind of interesting that you can do this kind of math with embeddings. Again, like these positions, these vectors are created during the training of the model. And this is kind of how you can like visualize more or less how the model may use these values of these vectors to understand like the world we live in or it lives in. The second part of the LM, as I said, are the weights that are basically like matrices and floating points that make up the transform part. So that's our black box. So we're not going to go into that much more. And this is it for this little small talk. So we talked about three files that make up the LM. The first is the inference engine, again like a tiny executable. The second one is tokenizer, basically an ASCII table. And the third one is our bin or save tensor file that contains the embeddings, which are the GPS coordinates of the tokens, and the weights for the transformer. If you like these talks, follow me on Twitter and other social media. My name is always Ronald Manick. And I would like to thank Ray, John, Natasha, Ryan, and Roderick for their feedback on these talks. And if you haven't tried running any local models on your computer yet, my app is called Pico AI Server. It's a free download on the Mac App Store. Please download it and see what you can do with like local models on your own computer. And if you do that, please leave a review and or a rating because it helps me getting the app noticed in the App Store rankings. And thanks so much.